Uh, you guys can see my screen?
Yes.
Perfect. Okay. So let's start. Okay. Yeah. Hello, everyone, and thank you, organizers, for inviting me to this TPM workshops talk. I wish I could attend in person, and hopefully maybe next year. So today, what I'm going to discuss is what I like to call clean, and I should not say this, but formal work with clear results that has some potential to be useful in a wide variety of practical applications. And another useful feature of this work that I'm going to present today, this work is about this problem called constrained most probable explanation problem, is that tractable models play a huge role in this work. And that's why I'm trying to present it at this workshop. And before I proceed, I want to acknowledge that this is a joint work with Sara Rouhani, who graduated a few months back, Rohith Peddi, who is my PhD student, and Tahrima Rahman, who is a research scientist at UT Dallas. So the problem I'm going to present algorithms for, and as I said, it's called the constrained most probable explanation problem. And our work in this task is inspired by applications in explainable AI, or XAI in short. More specifically, let me present application one, which is about finding explanations such that the decision made by a discriminative model does not change because of the explanations that are provided by the model. In other words, the task here that we are trying to address is to find explanations that conform to the discriminative models. So let's look at an example. Let's look at a real-world task. Let's say you are given an image and you are asked to classify the image. So in this case, let's say you are given a street sign, which is shown on the slide, and your task is to classify it either as left turn and U-turn not allowed, or just left turn not allowed. So for most image classifiers, if the image that is shown on the slide is given to them as input, this task is easy because the image is very, very clear, right? And the classification here is that no left turn is allowed or no U-turn is allowed. So let's make the task a little bit harder and make it into a real world scenario. So let us say that there is a gray patch on the traffic sign, either due to camera errors or something is being fuzzy. So now the task is not only to provide a class for the street sign, because the class is not that clear. So essentially either classify the street sign as no left turn or no left turn and no U-turn. But your task now is also to explain why you made this decision, okay? And the explanation can be a visual explanation where you just complete the image by filling up the gray patch. So the explanation might be, I classified this image, I should say, as no left turn and no U-turn because if I had completed the image would have looked something like that. So let us say that your AI system is equipped with 3 models, and we have, let's say, 3 subsets of variables, right? Decision variables, which in this case is a class variable. Evidence variables, E, which in this case are the pixels minus the patch. And explanatory variables H, which in this case are the pixels associated with the patch. Okay, so the 3 models here are a discriminative model, which we call R, which is good as classifying given the patch. Okay, so this model is good at classifying these images if they have patches in them. Then let's say we have another discriminative model which takes the whole image as input, which I'm going to call this model as Q, and is good at classifying complete images. And then let's say you have a generative model, which I'm calling as P. And what the generative model does is it's good at filling these patches, right? So good at filling or finding an assignment to value of assignment of values, I should say, to these variables h, such that E is given to you, right? So H is the patch and E are the remaining pixels. So now the same decision explanation task, in this case, can be defined as follows. Find the most probable assignment to the missing pixels using P, such that the decision made by R matches the one that is made by Q. Okay, so if the decision made by R was, let's say, in this case, that no U-turn or no left turn is allowed, right? Then you should complete the image in such a way that the explanation, right? So the completion of the image is nothing but the explanation, that the explanation matches the decision, right? So in many cases, what happens is that the generative model will not conform to these discriminative models, and the generative model is good at doing all these completions and explanations, and we don't want that situation to happen in the real world. Okay, so that's the task that we are trying to solve, which is generating these so-called same decision explanations. Second application that we are considering for this constrained most probable explanation problem, or the CMPE problem, is adversarial attacks on discriminative models. So we have a paper at this workshop and also at UAI, which looks at learning models that are immune to these attacks. But this is not about learning. This is a different problem. This is an inference problem where we are trying to attack a discriminative model. So let us consider, again, image classification task. And let's say you are given this street sign or given the speed limit sign, and you have to figure out the speed limit. Okay. So now let us say that you're given a discriminative model Q in this case, which solves this task, right? And also a generative model or a statistical model P, which generate alternative images that look like the original image. Okay, so think of the generative model P as, let's say, a similarity function, which takes an image as input. Let's say this image E as input, and outputs another image, let's call it E prime, that is semantically similar to the input image, right? So that is your generative or statistical model P, right, which outputs this E prime that is semantically similar to E. So under this two models, P and Q, the adversarial attack problem can be stated as follows, right? Find the most likely modification, E prime of E, according to P, right? So find something that is semantically similar to the original image, according to your probabilistic model P, such that the decision made by your discriminative model Q is flipped, right? So in this case, the discriminative model made the classification that this is nothing but a speed limit of 30. And now your task is to modify, right? So attack the discriminative model and modify this image of 30 to something else, which is as close as possible to the original image, such that the decision made by Q is flipped, right? So the decision made by Q in the second case, when I added these extra pixels to 30, is now a speed limit of 80, right? So we don't want our discriminative models to be prone to such attacks, but before we learn such discriminative models that are immune to the attacks, we have to actually figure out like how to attack the discriminative model, right? So this is the inference problem that we are trying to solve in this paper, in this work. So what I've presented are two interesting applications until now, right? This application about same decision explanation, which is generating explanations that match your decisions, and also this adversarial attack problem. And turns out that if you write these problems down mathematically, these two tasks are similar to each other and actually can be reduced to each other. And therefore, what we want to do is we want to study these tasks as a group rather than studying them individually, right? So in a way, what we want to do is we want to utilize and reuse algorithms for one task to solve another task. So we call this unifying task as this constrained most probable explanation task, or CMPE task in short. So mathematically, the first task, which is the same decision explanation task, is to find this explanation H, namely an assignment to the patch in our example that maximizes the probability according to the generative model P, such that the decision made by the discriminative model Q, which was 1 in this case, remains the same, right? So the probability of Q outputting D equals 1 is higher than the probability of Q outputting D equals 0 when the image is completed using H. The second task, it can also be written down as an optimization task, and actually a constraint optimization task, which is to find this semantically similar image E prime such that the decision made by Q is flipped, right? So because this is an attack, the original decision, let's say, was 1, and now we want to change the image to E prime such that the decision changes from a 1 to a 0. So the probability of D equals 0 is now higher than D equals 1. In fact, when we actually formulated these two problems as CMPE, we kind of realized that a large number of real-world tasks, including things like the nearest assignment problem, which seeks to find the nearest neighbor in terms of weight or probability in a probabilistic graphical model. Similarly, other tasks such as robust estimation and computing fair decisions can actually be reduced to this CMPE task, right? So the good news is that once I develop algorithms for CMPE, I will be able to solve many of these tasks using these algorithms. So let us get to the meat of the problem, right? And let me define the problem, the CMPE task, formally using graphical models or Markov network. And so what I'm going to do is I'm going to present a bit of background and notation before we do that. So let us say we are given a Markov network, which is defined by a triple X, F, and G. And the Markov network is the symbol M, where X is a set of variables, right? F is a set of log potentials, and G is the primal graph or the interaction graph that is associated with the Markov network. So in the example given on the slide, we have 5 variables, x1 to x5. We have 2 potentials, right, which are defined over x1, x2, and x3, and x4 and x5. And the primal graph is shown on the slide, right? So we have a potential over x1, x2, and x3. So that's why x1, x2, and x3 are in a Klee. And we have a potential over x4 and x5. And that's why x4 and x5 are in a Klee. An assignment or a configuration is nothing but an assignment of values to all the variables. So in this case, we have 5 Boolean variables, let's say, and here is an example of an assignment where we have assumed, actually I should say assigned the values 0 or 1 to each variable in X, right? So there are 5 variables, and so therefore we have these assignment to 5 variables. So the weight of the assignment to all variables is computed as the sum of the functions, right? So thus for our running example, if we project the assignment onto the 2 functions, we'll recover some real numbers, and the weight of the assignment is nothing but going to be the sum over those 2 numbers, right? So I'll project this assignment on the function f1 and project the assignment on function f2. I'll recover 2 values and I'll add them up, and that sum that I'll get, I'll call that as the weight of the assignment. So the probability of the assignment is nothing but the exponentiated weight divided by the normalization constant, and that normalization constant is also called the partition function of the Markov network. So given this background, let me now give you the problem statement of constrained most probable explanation, right? And as I said, like most of the problems that I described before can be reduced to this CMPE task. So you're given these 2 PGMs, let's call them M1 and M2, that are defined over the same set of variables, and you're given a real number Q, right? And now your task is to find an assignment to all the variables, right? So to find an assignment to X such that the weight of the assignment is maximized according to M1, right? So this functions F are associated with M1. So what I want to do is find an assignment such that the weight is maximized according to M1. such that the weight according to M2 is smaller than Q. Okay, so that's the CMPE task, right? So you have a maximization over the graphical model subject to a global constraint, which is defined by another graphical model. So the problem is clearly NP hard because even the unconstrained version, which is nothing but the most probable explanation task in graphical model, is known to be NP hard. However, turns out that this CMPE task, because of this constraint, because of this global constraint, I should say, is much harder. So even on the simplest type of tractable models, right? So think about a tractable model that has no edges, or a model in which all variables are mutually independent, I should say, of each other. CMPE problem turns out to be NP hard. Okay. So let me try to make the problem definition more concrete using an example. So let us say that you are given two models over 3 Boolean variables, x1, x2, and x3. So the first table shows the weights of the 8 assignments according to x1, x2, and x3. So according to model M1, I should say. And the second table, which is on the right, shows the weights according to the second model M2. And here I'm assuming that this real number Q is equal to 6. So the task is to find an assignment having the highest weight according to M1, such that the weight according to M2 is bounded by 6. So thus you can see that if you just look at the constraint, the 4 marked assignment actually satisfy the constraint according to M2, right? So the weight of the assignments of these 4 assignments is smaller than 6. So if we project these 4 assignments on M1, we can see that the maximum weight according to model M1 is now 7, right? So that's the optimal solution. So the unconstrained version of the problem in the optimal solution would have been 9, right? But the constrained version of the problem, the optimal solution is now 7. And that's the assignment. So the good news is that CMPE can be easily encoded as an integer linear program, and thus we can use off-the-shelf solvers such as, actually I should say Groby, which is a commercial solver, and Skip, which is an open source integer linear programming solver to solve it. However, it turns out that we can actually compute and we can actually do better. We can come up with like better algorithms for CMPE, which is what this talk is all about. So now let me give you some more concrete examples of applications of CMPE and how we can encode the same decision task and the generating adversarial examples task as CMPE task. So a common inference problem in graphical models is finding the most probable explanation. The decision preserving explanation problem, or the same decision explanation problem, finds the most probable assignment or most probable explanation of a given partial assignment according to the generative model, such that the same decision is made according to the discriminative model, right? So the generative model is now associated with F, and the discriminative model is also associated with F, but it computes different things. So given a graphical model that its random variables include, let's say, decision, evidence, and hidden variables, and given a decision made on some observed evidence, the decision preserving MPE task is to find an assignment to all hidden variables such that a decision based on the hidden variables and the same observed evidence would be the same. Okay. So decision preserving task, as it turns out, is nothing but a special case of CMPE. So in the figure on the slide, we want to find an assignment of values to all variables other than the decision variable D in this case, and observed variables X and Z, such that the probability of the assignment is maximized, right? So at a high level, we want to find this assignment to Y and W such that the same decision is made. Okay, so if what MPE assignment might do is it might actually flip the decision from a green to a red. But if we now solve the CMPE task, which is saying that, oh, make an assignment to Y and W, but when you make that assignment, the decision to D should not be changed, right? So if we made this orange assignment to Y and W, it turns out that the decision D remains the same. Okay, so that's the task that we are trying to solve. Make an compute explanation such that the decision does not change. So next we consider the task of actually rendering adversarial attacks on discriminated classifier, right? So these attacks can be viewed as manipulating the decision of a classifier by minimally changing the test samples, okay? So consider a discriminative classifier, let's call it a linear SVM or even a logistic regression classifier, which is expressed, let's say, as a log linear model, right? Or a Markov network, which outputs the decision 9 if its weight is non-negative, and outputs the decision not 9 if its weight is, let's say, negative or less than 0. So we can think of this test sample X and its associated class D in this case, right? So this is the test sample and its associated class D as a constraint being encoded by the classifier, right? So the discriminative model always goes into the constraint. And our goal in rendering an adversarial attack is to find an assignment, let's call it X prime, such that the decision flips from D to D prime, right? So what I want to do is minimally modify this 9 such that the classifier, which is this linear SVM in this case, no longer classifies it as 9, but classifies it as something else, right? So what I can do here is I can use these functions f to define a similarity measure, which says that if the distance between the image that you generated, which is a modification of 9, and the original image, which is this 9, is large, then I will give you a large penalty, okay? And if the distance is small, my penalty will be small. So now your task is to find this modification of 9, right, using these similarity functions, such that the decision made by the classifier is flipped, right? So now that is nothing but an adversarial attack on the classifier. And turns out that this is nothing but a CMPE problem. Again, the CMPE problem is nothing but you're maximizing according to one graphical model, such that the constraint is satisfied according to a second graphical model, okay? So both these problems that I just mentioned can be easily formulated as computing CMPE on a graphical model. So next up, let me give you a briefly give you a flavor of lower and upper bounding methods for CMPE, starting with lower bounding methods, right? So now it comes to the main thing that I want to present, which are algorithms for solving these CMPE tasks, right? So you can use actually integer linear programming solvers off the shelf to solve this task. But in many cases, actually, I'll show that by using specific graphical model techniques, you can solve this problem much faster and better. So the first algorithm that we have developed is a lower bounding algorithm, right? And the second algorithm that I will show is an algorithm that we have developed, which is for computing upper bounds. So we have developed this novel algorithm, which I'm calling anytime CMPE, for computing lower bounds on the optimal value of CMPE, or more generally, to compute a good feasible solution. So our algorithm, what it does is leverages a special version of knapsack problem and a graph property called k-separator, right? And what I'm going to do is I'm going to present these two things that our algorithm leverages, which is this multiple choice knapsack problem and also the k-separator concept. So in a short, a MCKP problem, or a multiple choice knapsack problem, is nothing but a standard knapsack problem in which we are given actually multiple bins instead of a single bin. So we are given m bins of items, right? And each item will be associated with a cost and will also be associated with a profit, right? So the bins are indexed here by I, and the items in the bin are in each bin are indexed by j, right? So Cij is the cost associated with item J in bin I, and Pij is the profit associated with item J in bin I. And we are also given a knapsack, which has this capacity Q, okay? So now the task is to select exactly one item from each bin such that the total profit is maximized. However, the total cost of the items is now bounded by Q, right? So that is a multiple choice knapsack problem. So you might be familiar with regular knapsack problem, right? Or conventional knapsack problem in which like you're not given these multiple bins. So this MCKP problem is actually NP hard, right? And it's a well-known NP hard problem. But the good news is that we have large number of greedy algorithms for solving these problems efficiently in practice, right? And actually it turns out that if the weights are real, so I should say in this case, costs and profits are real, then this problem is strongly NP hard. But if this costs and profits are actually integers, then this problem can be solved in, this problem is, I should say, only weakly NP hard and can be solved in pseudo-polynomial time. So in our work, we actually used a greedy algorithm to solve it, which is linear in the number of items. And the good news about this greedy algorithm is that it actually has a 4x5 approximation guarantee, right? So now we can take these guarantees and directly apply them to CMPE if we somehow found an encoding that encodes a CMPE problem into a MCKP problem, okay? So here is how we can perform this encoding, right? So what I'm showing here is how to encode CMPE as this multiple choice knapsack problem. So in this case, now any solution to MCKP could now be a solution to our CMPE task. So this example shows a CMPE task over our graphical models M1 and M2. And we are given, let's say, a value Q, which is 10. So the combined primal graph actually combines the two graphs G1 and G2 and adds an edge which represents, which are present in one graph, but not present in the other graph, right? So what our encoding does, it builds MCKP by creating one empty bin for each of the connected components, right? So there will be a bin associated with this connected component and a bin associated with this connected component of the primal graph. And then for each component, the encoding creates items with costs according to the two functions f and profits according to the g functions, right? So the first graphical model M1 is used to create these profits. And the second graphical model M2 is now used to create these costs because the costs are associated with the constraints. And the capacity of the encoded knapsack is equal to Q in this case, which is nothing but 10. So MCKP is strongly NP hard, as I said, unless the number of items in each bin is bounded by a constant, right? And in CMPE, the number of variables in each component needs to be bounded by a constant, right? The issue is components are not bounded in most PGMs, right? So the solution is highlighted here. And what I want to stress is that the main virtue of this MCKP encoding, where we take like CMPE task and model it as MCKP task, is that we can solve CMPE using MCKP algorithms and utilize actually 30 plus years worth of research in the operations research community and also in the optimization community, actually now to solve CMPE. However, unfortunately, life is not that simple, right? So in our encoding, there is an issue which I kind of alluded to briefly. And the issue is that the MCKP encoding works, as in the encoding is practical, if and only if the size of each connected component in my graphical model is very small, right? So there are very few variables in each connected component. So to solve this problem, and in general, like graphical models that we use in practice are not going to satisfy this constraint, right? So we'll have a fully connected model in this case. So to solve this issue, what we leverage is this graphical structure of PGMs, and propose to bound the size of the components by using cutset conditioning, specifically by using a graph concept called k-separator, right? And what I'm going to do is I'm going to demonstrate this cutset conditioning approach, or this k-separator approach using this graph. So let's just say that you're given this graph, and now I give you a value of k, which is 7, and I ask you the following question. Find a subset of variables such that when you remove those variables from the graph, the remaining graph is such that each connected component only has 7 or fewer nodes in it, right? So in this case, if I remove these 3 variables, which are highlighted in gray from the graph, I can take them out, and now each connected component has fewer than 7 variables in them, right? So if that happens, I can take this problem and now encode it as a MCKP task and use MCKP algorithms now to solve it, right? So that is the method that we are going to use. Essentially, take this separator, do cutset conditioning or conditioning on this separator, and then solve the CMPE task for each assignment of values to the separator. Okay. So we can either solve this problem by doing some random sampling or local search over these assignments, right? And the good news is that the time complexity of our algorithm will be exponential in the size of the separator, but if the size of this k-separator is bounded, so the size of k-separator in this case is actually 3. If the size of the k-separator is bounded, then we have a polynomial time algorithm actually for solving CMPE. Or actually, I should say polynomial time algorithm for computing really good approximation guarantees on CMPE. So by using these 2 graph properties, or I should say using the graph property of k-separator and using MCKP solvers, we constructed a new solver. And we found that actually this new solver is much better than Skip, which is an open source integer linear programming solver in many, many cases. Right. So here is a problem which is from the UAI repository that is shown. On the x-axis, I'm plotting time in seconds. And on the y-axis, I'm plotting the value of the objective function. So higher is better in this case. And here are the various lower bounding techniques where I'm changing the value of k, right? So I'm changing from k equals 1 to k equals 9, and you can see the results on the slide. Skip is this particular line, and as you can see that the objective value, so Skip is an anytime algorithm, and the objective value that is reached by Skip is much smaller as compared to the new CMPE algorithms that we have discovered in our investigation. On another set of benchmarks where we assume that M1 is equal to M2, so the 2 graphical models, M1 which specify the optimization problem and M2 which specify the constraints are the same. So it turns out that
sorry, we have 5 more minutes.
5 more minutes, yeah. Okay. Yeah. So actually it turns out that these 2 tasks are, these 2 CMPE problems are actually much harder, right? And so what happens is that on these harder problems, we can see that Skip, the difference between Skip and our algorithm, so I'm plotting error in this case, is much larger. When we have extreme parameters, actually Skip cannot even generate really good solutions, while our algorithms actually are able to generate good solutions, right? So extreme parameters are these graphical models which are actually very, very hard in practice. So we also come up with algorithms for computing upper bounds on CMPE, and I'm not going to go over the details of this algorithm for lack of time, but the idea in these algorithms is to actually use MPE and MCKP solvers to come up with actually near optimal solutions, right? So instead of computing lower bounds, which our previous method computes, these new methods actually compute upper bounds, which are as close as possible to the optimal value. So what they do is they actually use this two methods from optimization called Lagrange relaxation and Lagrange decomposition. So the Lagrange relaxation method actually, what it does is it converts the CMPE problem into a MPE problem by adding this extra lambda parameter, which is and computing this Lagrange relaxation, and then finding the optimal value of lambda, which is minimizing the lambda over this Lagrange, will give you the optimal value, right? So that's the Lagrange relaxation method that we have come up with, and this was a paper that was published last year at NeurIPS. In many cases, what happens is that the graphical model itself is intractable, so MPE task is also intractable. So in that case, we can use mini bucket-based elimination algorithms, which are these algorithms that were proposed in Arena Decter's group for solving these problems and computing upper bounds on CMPE. So I'm not going to go over the experimental results for these upper bounding algorithms, but the point here is that there are two types of upper bounding algorithms. One are based on knapsack, and the second one, which are based on mini bucket elimination. And sometimes the knapsack algorithms are better, and sometimes the mini bucket based algorithms are better, right? So we have kind of like best of both worlds, where we are using graphical models techniques sometimes, and sometimes we are using kind of techniques developed in the knapsack or operations research literature. Okay, so in summary, what I have maybe done here is trying to propose a problem called CMPE, which is a unifying inference problem for graphical models. And at least what I've shown to you, that CMPE has several estimation and explanation applications. Many problems in the real world can be actually be just encoded or cast as this CMPE task. Applications such as explanations with that provide the same decision, image completion task, and also adversarial attack task. In our work in NeurIPS 2020, we have proposed CMPE-based lower bounds, and in the work in NeurIPS 2021, we have proposed upper bounding methods for CMPE. And these methods actually work very well on things like the MNIST dataset. So in future work, what I want to do is actually come up with algorithms for solving a much difficult version of CMPE, which I'm calling CMAP, where so in our current situation, the task is a maximization task. But in the CMAP case, you'll have a task which is a maximization plus a summation task, or a max sum task, which is known to be much harder, because you have to sum out all the variables that are not involved in the query or not involved in the explanation when we are trying to solve this CMAP task. Okay, so that's like some of the algorithmic issues that we are going to try to address. We also want to make CMP much harder. So right now we have only considered one constraint, but eventually we want to solve CMP tasks that have multiple constraints. So you're given like a collection of graphical models, and each graphical model is giving you a constraint, and now you're optimizing such that all constraints are satisfied. We have considered many applications of CMP, such as generating adversarial attacks on neural networks, which are much complicated classifiers. So in our current work, we only looked at linear classifiers. And finally, we are trying to learn tractable models specifically for solving CMP tasks more accurately, right? So go beyond the so-called simple optimization task and simple summation task that we have looked at in the tractable models community, and move to more complicated constraint optimization tasks for tractable models. Okay, so that's my talk, and hopefully I finished on time. And if you have any questions, please.
Thank you, Vibhav, for a very nice talk. I think we have time for a couple questions, maybe questions from the audience, or if anyone on Zoom has questions, you can drop them on chat.
Hi, Vibhav. Thanks again for the super nice talk. I have like perhaps a stupid question. So what happens when you have continuous variables? Is it true that you have a linear program? And if that's correct, could it be that for some specific structure of your problem can be easier to solve? So in the general case, we know the complexity for the linear program, it's not great. It should still be hard, but for specific cases, we might do this.
So I have not looked at continuous versions, but actually you're right. Like actually for some models, like the Gaussian models, for instance, right, it will be a case of linear program. But if you have like mixtures of Gaussians and things like that, more sophisticated models, you are still going to have these variables that you need to optimize, right? So you're right. Like, so in some cases, yes, linear programming, right, you cannot beat that. But in many other cases where you have these more sophisticated models, we'll have to go to techniques like the ones that are proposed.
Okay, let's thank the speaker again.
Thank you, guys.